Now let's look at the case of vertical asymptotes. So just to kind of recap here, I guess this would have worked. So in this type of example, we are going from a fixed value that's defined, and then you're approaching infinity where the graph approaches zero. Could go like this as well. And then you want to add up that area and see if that integral converges or not. The next case is this vertical asymptotes, and what happens when you go from say A and then you approach a vertical asymptote like this. So you want to find this area. Now, substituting directly for A or B in this case would be undefined, so that would be improper. So you need to approach B on the left. So we're going to do a limit and approach B on one side, or vice versa. For this case, you're at B and you want to approach. So T is coming in like this, and you want to approach A on the right, or whatever constant you use. Constant doesn't matter. So that's this next case. And so you could end up integrating over a vertical asymptote, and then that would be improper. That would be kind of wrong, actually, if you did that. Usually they stop at, say, 3 or something like this example, but you got to approach on one side or the other. So let's look at this case, or this example. Suppose you have the integral from 0 to 3 of 1 over the square root of 3 minus x dx. And so we can see if you just were to integrate and substitute in. This is the function. Like, you have a function of whatever that is, but it's undefined at 3. So plugging in 3 here, it would give you, you can't do that. Obviously you got to integrate first, but that doesn't work. So you need to take a limit. So we can see here that it's improper because x cannot equal positive 3. The radicand, though, of a radical needs to be positive. So we need to you can't put in like 2.99 either. You got to put in everything I'm sorry. You can't put in here. You can't put in 3.001. You got to approach on this side. So put in values like 2.999. If you put in 3.01, then it's negative, and that would be imaginary. So this is an improper integral. This, just to get this all down for you, is an improper integral. And so what you do is you then say this is equal to, and you take a limit as t approaches 3 on the left, and then you substitute in your values. And then you go 0 to t of 1 over square root of 3 minus x dx. Okay, so that's your setup. And so I'm going to kind of speed this up. So do the integral, and you'll get the limit as t approaches 3 on the left, and then it ends up being negative 2 square root of 3 minus x from 0 to t. So make your substitution. It's really not that bad. Just make u to be 3 minus x. You get a du. You have a negative in front. Make this into negative a half, and then you'll get that. Okay, so then substitute in your values. So that's the limit as t approaches 3 on the left of negative 2 square root of 3 minus t plus 2 root 3. And so we can see as you approach 3, this will go to 0. So we can say that this is going to approach 0. And so you get this is equal to 2 root 3. Now, what's I need to point out here is if you didn't bother to do this, you still would actually get 2 root 3. Wouldn't you? Like if you just put 0 to 3 here and you plugged in 3, that would actually be 0. But the format would be improper. Like it would not be a correct form. It would be mathematically wrong, even though you get the correct answer. So as you're communicating your work, you would have a logical breakdown and there would be a logic problem. You would not imply the other because it's improper, because you cannot actually plug that in here. Now, so this you got to be careful. This is a lot about notation, but it's also what you're really communicating when you do this one. Okay, let's do another one. Okay, we have a couple here. So this next one would be a problem. Let's look at this example. You have the integral from negative 2 to 7 of 1 over x plus 1 to the 2/3 dx. And this is an issue. This is an issue because where is this function defined? It's defined everywhere except negative 1. X cannot be negative 1. But look at my limits of integration. My limits go across negative 1. Not a good idea. I can't do that. So this, I mean, you can ask what that limit is, or the integral is, but you need to break this up and approach on either side of that negative 1. So what you would say then is this equals the limit as t approaches negative 1 on the left, and then we'll do plus on the right. So this will go from negative 2 to t of 1 over x plus 1 to the 2/3 dx, and then now you do plus the limit as t approaches negative 1 on the right. And you now go from t to 7 of 1 over x plus 1 to the 2/3 dx. So now you're doing this properly, and you'll do your limits how we need to do them. So this equals the limit as t approaches negative 1 on the left, and then we do this integral. So I actually did this off to the side with just a u. So if you pick u to be x plus 1, your du is dx. But so you really are doing the integral of u to the negative 2/3 du. I'll bring this over a little bit for you. And then that equals u to the negative 2/3 plus 1 over negative 2/3 plus 1 plus c. And so this ends up being 3 when you flip that up, right? Because this is 3/3. Right, so you have 3/3, and so it's 1/3, and it flips back up to give you 3 u to the 1/3. So this is okay, I gotta try that again. There, yay, did it. The integral, just to an aside there. So, and both of them will be like that. So we can just write that in. And that's a cube root. You can just write it as, normally we'd say cube root. So that's 3, and then we'll go ahead and say that's a cube root of x plus 1. Just put the cube in there. And we evaluate from -2 to t. Okay, so you can see how this is going, right? So this is a good time to pause this and work ahead and see if you get this. So 3 and then cube root x plus 1 t to 7. Now substitute in and evaluate. Okay, so you get this is equal to, the limit as t approaches -1. 3 cube root of t plus 1 minus 3 cube root of, that's a cube root. Be careful, it's 3 times that cube root. And that'll be -1. And then plus, and I'm going to have to bring this closer together. And put that in brackets. Okay, and then the limit, t approaches -1 on the right. And so that'll be cube root of 7 plus 1 is 8. So that actually works out nice. And then minus 3 cube root of t plus 1. Okay, and so you get, let's see what happens. So this guy here, this, so -1 here, this is approaching 0. And this is approaching 0, same thing. So you're evaluating the limit, the radicals. So that'll be a 3 here. So negative, and that's a -1, so it becomes a 3. And then plus 3 times cube root of 8 is 2, right? So that's a 2 there. So it ends up being 3 times 2. So that's just 6, which is equal to 9. So that's what's going on. So you have to go around whatever the graph does. In this case, I'm not going to pretend we don't know what the graph is. You have your -2, and you must approach on either side. So you got to approach like this and like this, and then get a value. So it is interesting to see that if you just substitute in those values, you will get the same result. But the logic up here would be wrong. Okay, it would not be a connection without doing this limit. Okay, let's do another one. So the integral, this one goes from -infinity to infinity. This is, I wanted to throw in this case because it's actually it's kind of cool. You see what happens, but also, what do you do if you go from negative infinity to infinity? So that graph actually looks like this. Okay, so if you graph 1 over x squared, you get 1 over 1 plus x squared. Basically, at 0, you get 1. So you're up here. Let's just call that 1 right there. And then it does this sort of thing. And then it goes down. And it's symmetric. I can't draw it symmetric, but it's symmetric. So we're trying to figure out the area of this. What's this area? Like that. So you need to break this up. I mean, you could come down here and say, well, let's just stop at -2 and then do your integral. But that would be silly, wouldn't it? I mean, you want to stop at something that's reasonable. And if it's symmetry, stop at wherever it's symmetric. So we're going to stop at 0. Would make sense. You don't have to do limit on either side of 0 because it's defined. But you need to break that up and go from negative infinity, and we'll stop at 0 of 1 over 1 plus x squared dx. And then do that again. Go from 0 and then approach infinity. All right, so then let's put in our limits. That's now we're approaching infinity again, right? It's a horizontal asymptote. So t approaches negative infinity, and we'll go from t to 0 of 1 over 1 plus x squared dx, plus the limit as t approaches positive infinity, integral 0 to t, 1 over 1 plus x squared dx. All right, so what is that integral? When you integrate that, what do you get? Do you recognize that? We should start recognizing these integrals by now. Okay, so there's my infinity. That is tan inverse. So tan inverse x, we're going from t to 0, plus the limit t approaches infinity, tan inverse x from 0 to t. And then you got to be really careful when you substitute this in because you get different values. So tan inverse, and you may want to look this up, but when you put in 0, you get 0, and then it's minus. And then if you approach negative infinity, you get negative pi halves. And then similarly, when you approach, and I'm kind of skipping a step here because I know what's going to happen. I'm going to substitute in and take a limit when I approach positive. So basically, tangent looks like that, and it approaches those horizontal asymptotes. So look that up. You can look up the graph directly. That's how I like to do it. And you end up with pi halves. So you get pi halves and then 0. So you add that up and you get pi. So the area under that curve is pi. I think that's pretty cool. I mean, you're taking a rational expression that has nothing to do with trig, just as a function, and you add everything up and find an area. I mean, trig comes up in the antiderivative, but the area under that curve is pi. Isn't that neat? That is so cool. I like that. Okay. That pretty much hits all the different cases you will see for improper integrals. And I believe that pretty much wraps up chapter 8. I did do an example of Gabriel's horn. You can look at the notes on that one. I don't think I'll do a video on that. My notes have that. It's kind of interesting. oops, I'm going to go ahead and paste that over, just talk about it. Don't worry about those. I have different ones I want you to do. So Gabriel's horn. So this is an interesting result. I think there's other names for it, but that's the one I found in the book. So Gabriel's horn, I'll just talk about it. Very interesting concept here. So you have 1 over x from 1 to infinity. So it's stopping right here, and you're going like this. But then then back in chapter 6, we're revolving that thing. Okay, we're revolving this thing, so it looks like a horn, right? And it goes off, and it just gets smaller, goes to infinity. This first calculation is the volume inside. And so you do pi times the radius, which is 1 over x squared. And you go from 1, and then you approach infinity. So you can't really do this until now, but now we are revolving it. Okay, so when you do, you do your limit and all that, and you get pi again, which is very interesting. So you get pi is the volume inside this infinite horn, if you will. Okay, then if you look at surface area, you look at the surface area of this thing, you're looking at this piece, and you're approaching infinity. So, and then you're revolving that piece. So you can look this up again, but you get 1 in the derivative. Okay, so I worked that all out here and evaluate. Now this, I think, I forget what I showed you. So this is greater than 1. Okay, so I had to, this is an argument basically, but since this diverges and this is greater than 1, this has to diverge. So it has, and I'll say that again, it's a little more slow. So when you do this, you get this integral. We already showed that 1 over x diverges above from a constant to infinity. And so if you put in a square root of something that's greater than 1, you can see that, right? 1 plus something that's a little bigger will be greater than 1. So this is adding 2 pieces of that. It's not getting smaller. And so since this diverges, the whole thing must diverge. When I'm saying star there, since 1 over x diverges, then this must diverge. Therefore, you have infinite surface area. So you have finite volume inside, but infinite surface area. Crazy result. And this infinity stuff just starts blowing your mind away. It's quite a trip.